Hey, Hallie, happy last week of school. I wanted to just go through past assignments, past assessments. I know I made comments, but I wanted to make video comments to support them, just to give them more concept, maybe a familiar voice. It's probably easier than trying to read my chicken scratch. So, yeah, if you want to resubmit these, great. I will definitely regrade and get your grade updated. So in number one, you did a great job calculating the angular acceleration. But B, net force equals mass times acceleration. That'd be great if I were just pushing this disk on the ground, right? I'd have a force applied, I'd have a friction force, I'd have that total mass, and then I'd have linear acceleration. But that's not what we've got on. We've got something rotating due to a torque. So I have this comment only if you're going to slide the object. But if we're going to rotate, we can think of it as like a merry-go-round. If I apply a force at a certain radius, the merry-go-round spins, right? So that force at a radius is a net torque. The mass is not the mass of the object, it's that because mass is inertia, right? That resistance to translational motion, but that resistance to rotation is rotational inertia, which is I. And then it's not about translational acceleration because the disc is not, or the merry-go-round's not sliding across the park. It's just angular acceleration. So the equation that's going to drive part B is net torque times I, which is rotational inertia, times angular acceleration. So net torque equals I alpha. Okay. So let's see what's down low. This is the hollow cylinder rotating. What are our energies? An object has energy if it has height. So you've got that maximum height where it's not rotating and it's not rotating or moving translationally. So great. That's going to equal its linear or translational motion because a rolling object like a bowling ball has energy. But a spinning object also has energy. Okay? So the amount of energy for this rolling object is split between its translation and its rotational kinetic energy. And that rotational kinetic energy should be 1/2 I omega squared. You got to make sure you've got the correct I, rotational inertia, for a hollow cylinder. I believe that should just be mr squared. Okay? And then you've got to have the right omega. Now, there was a video to support kind of that work of canceling some stuff out. So take a look at that video as far as energy and rotation. And the last thing is related to a conservation. I have conservation of L. Well, L stands for momentum. Okay. It's a conservation momentum thing. Let's think of conservation of energy versus conservation of momentum. In conservation of energy, we only talked about one object. Do you remember that? Like a pendulum. We talked about the pendulum changing energy states. Or we talked about a ball on a spring being compressed. It had spring potential energy, and then it had kinetic energy, and it went to potential energy once it was top of its motion. It was all about one object, right? In conservational momentum, right? It was about two objects colliding translationally, right? When we talked about a train car running into a stationary one and they combined and they went off together, okay? Well, here we've got a rotating object and then an object not rotating. They collide inelastically, they become one rotating object. And so, how fast are they going from that point on, right? So, it's not conservation of kinetic energy. That would be one object. This is conservation of momentum. So if you wanted to rework and go through that and rework that, no problem. Let's see if I can get out of this full screen. If not, I just did a great, awesome, fantastic video for no one's purpose.